Hello students, welcome back. Now we'll study about the thermal effects of electric current. This will give us the answer of why does an electric circuit heats up, how much does it heats up, and what is the relation between electric power and electric energy. So let's start.
We will now move on to the second last topic of current electricity, that is thermal effect of current. So for thermal effect of current, we have Joule's law, that is the statement in accordance with our observation. And what is the observation? I will tell you after the statement. When electric current is passed through a conducting wire, the electrical energy is converted into heat energy. This effect is called heating effect of electric current. Now the observation which I was talking about is whenever we use an electrical appliance for a while, we feel that the electrical appliance is getting heated up or it's warm before or let's say after prolonged use. So this is in accordance with the Joule's law. So as Joule's gives the statement about the heating effect of electric current, so it's also called as Joule's heating, and the corresponding expression for the given heat is I square RT. Now where I is the current, R is the resistance and T is the time in seconds. Now we move on to the cause of heating of the conductor. So the basic cause of heating is due to the constant collision between the charge carriers inside the conductor. When the electrons and the atoms they collide, or when the electrons collide with other electrons, they impart the kinetic energy, or they give the part of their energy to the others. So when they gain extra energy, that is extra kinetic energy, they start to vibrate rapidly, that is at a higher rate. So this results into high temperature or increase in temperature. So that's the reason behind heating of the conductor when the current is passing through it. Now, to understand in a much better sense, you need to visualize the motion of the charge carriers, or let's say how the current moves inside the conductor. So the analogy which can be close enough will that be of water falling in the water. That motion is kind of similar to the motion of the charge carriers inside the conductors. So now we move on to electrical power and electrical energy. Now electric power is the rate at which the work is done by electric current. So it's given by P VI, or P is equal to I square R, P is equal to V square R. So if you have to use P is equal to VI, just make sure that you do know what is the voltage and what is the current in this prospect. Voltage is the voltage across the element of interest, not the total potential difference. Same goes for these expression. Now, if you have a closer look at this particular expression, that is P is equal to I square R and P is equal to V square by R. In this expression, my power is proportional to the resistance. And in this, I have power proportional to 1 by resistance. That is, these two statements contradict each other. Either my power is proportional to R or my power is inversely proportional to R. One of them has to be true. But make sure that when I say power is proportional to R, I'm keeping in mind that my current is constant, I square is constant. Similarly, when I'm saying power is inversely proportional to resistance, I'm keeping in mind that my voltage is constant. So these are two different scenarios when you're trying to make out a statement out of it, that is P is proportional to R and P is inversely proportional to R. So this is the common mistake which students do make. So make sure this does not happen. So SI unit of power is obviously watt, and the other units which we use often is kilowatt and horsepower. So the different relationship between the different power units are given like this, that is 1 kilowatt is actually equals to 1000 watt and 1 horsepower is equal to 746 watt. Now electric energy. Electric energy is the total work done by an electric current in a given time. So we have power with ourselves, three different expressions for power. So if we just introduce the factor of time to power, we will get the total energy which we have consumed. So E is equal to VIT, simply P into T. Again E is equal to I square RT, same as that. P is equal to V square by R, E is equal to V square T by R, same as R. Now commercial unit of electrical energy is kWh or kilowatt hour or BOTU. So kilowatt hour is basically the commercial unit. In accordance with that, we pay our electricity bill. That's the same unit which you see in your electric meter. And that is 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joules. That is, what is the amount of energy consumed in 1 hour if you have a power of 1000 watt? That's equals to 3.6 into 10 to the power 6 joules. Now, let's study an example. So I have a question over here, that is 360 watt light bulbs are mistakenly connected in series to a 120 volt supply. Assume the light bulbs to be rated for 120 volt single connection. With the mistaken connection, the power dissipated by each bulb will be. For this, we need to have a corresponding diagram. That is, let's say we have mistakenly connected 3 bulbs. So this is my bulb number 3, and these 3 are being connected to a power supply of 120 volt. So we can definitely say that as these 3 bulbs are identical in nature, 40 volt will be over here, 40 volt will be over here, and 40 volt will be here. Now we need to make sure what is the power dissipated by each bulb. So P is equal to V square by R. So it gives me that P dash by P is equal to V dash square by V square. Now we know that P is the power of the bulb, V is the potential of the bulb, that is potential across the setup. So we can find out that the P dash is equal to P times V dash is equal to 40, V square is equal to 120 square. So I have over here. So as we know the P is equal to 60, we will put 60 over here. So it's 60 times 1 by 3 square, which comes out to be 6.67 watt. So this is my final answer.
So we just learned about heating effects of electric current and the Joule's expression for that heat given. We also studied about electric power and electric energy and the mathematical expression corresponding to it. And we also studied about the commercially available units of electric power. So in the next part, we will study about electric fuse and MP theorem. So stay tuned for the next part.